Welcome to the Explainer. Today we're diving into the communication crisis, I/O interfaces and DMA. Right now there is a fascinating, almost completely hidden crisis happening inside your machine. It's the huge gap between blazing fast processors and, well, relatively sluggish peripheral devices. Imagine having a supercomputer for a brain, but you're forced to communicate through a slow drip of information. That's exactly the problem we're unpacking today, and we'll see exactly how computer architecture bridges this enormous gap. Okay, let's dive into this with just one number. 1 million. So what does this actually represent? Well, if you have a modern CPU running at 1 gigahertz, it's executing an instruction every single nanosecond. But if you press a key on your keyboard, which operates at roughly 1 kilohertz, that single keystroke takes about 1 millisecond to register. During that one tiny millisecond, your brilliant CPU is just sitting there idle, waiting for 1 million clock cycles. Literally, a million wasted opportunities to process data. When we compare these speed scales, you can really see the staggering differences at play. We've got the CPU operating way up there at 1 gigahertz. Down below, there's a magnetic disk running at maybe 5 megahertz, and that keyboard crawling along at 1 kilohertz. Without a dedicated hardware solution to bridge this massive gap, this sheer mismatch brings your entire system's throughput to an absolute grinding halt. If the CPU had to wait for these devices to respond directly, your computer would feel agonizingly slow. So how do we actually fix this? Well, enter the I/O interface. Think of it as the ultimate global summit translator. Imagine you're at an international summit and you have leaders speaking entirely different languages at entirely different speeds. They obviously can't communicate directly, right? They need an earpiece translator to buffer and convert the information. In your computer, the I/O interface sits exactly in the middle between the fast CPU and the slow peripheral devices, bringing harmony to components that simply cannot talk to each other directly. And this brilliantly illustrates that the reason they can't talk directly isn't just about speed. It's actually about the very physical nature of the devices themselves. Look at the CPU. It's purely electrical. But your keyboard? It's electromechanical. And a magnetic disk is, you guessed it, electromagnetic. The physical signals they create are fundamentally different. The I/O interface uses specific conversion circuits to perform necessary hardware-level signal conversions. It translates those wildly different physical signals into the clean electrical digital logic that your processor can actually use. Plus, it's a matter of data formatting. Your CPU is probably a 64-bit powerhouse, right? It consumes data in massive parallel 64-bit chunks. But meanwhile, a keyboard sends data serially, just one tiny 8-bit character at a time. The interface solves this mismatch by maintaining local buffer storage. It patiently collects those tiny 8-bit serial streams from the keyboard, groups them together in its local buffer, and then packages the whole shebang into a neat 64-bit parallel data word that it hands over to the CPU all at once. Let's move to the evolutionary timeline and see how this builds across the 3 phases of data transfer. Obviously, computer architecture didn't solve this bottleneck perfectly on the first try. We evolved through 1. Programmed I/O, 2. Interrupt-driven I/O, and 3. Direct memory access, or DMA. Let's contrast those first 2 early methods. In programmed I/O, the CPU is constantly polling the device. It's basically constantly asking, "Are you ready? Do you have data?" It's incredibly inefficient and wastes millions of clock cycles. To fix this, engineers created interrupt-driven I/O. Here, the CPU works freely on other tasks, and when the peripheral finally has 1 byte of data ready, it literally interrupts the CPU to hand it over. This definitely frees the CPU from polling, which is a great start, but generating a whole interrupt cycle for every single byte still creates massive overhead for moving bulk data, like reading a file from a disk. So, the crucial point is we need a way to move bulk data without bothering the CPU for every single tiny byte, and that brings us to direct memory access, or DMA. DMA is a dedicated hardware mechanism allowing peripheral devices to transfer bulk data directly to or from main memory, completely without CPU intervention. It is absolutely the crown jewel of system throughput and the perfect hardware solution for heavy data lifting. With DMA, the CPU acts kind of like a highly efficient boss delegating a task. It doesn't do the heavy lifting itself. Instead, it just sends a quick command to the DMA controller with 4 basic pieces of info: the I/O port number of the device, the target starting memory address, the total byte count, and the read or write control signals. Once the CPU delegates these starting coordinates and the size of the job, it completely steps away to go do other work. So how does DMA actually do the work behind the CPU's back? Well, it uses a strict handshake protocol. First, the DMA controller sends a hold request to the CPU, asking to temporarily hijack the system bus. The CPU finishes its current tiny task and grants access with a hold acknowledgement. Now the DMA is running the show. The slow disk transfers data into the DMA's local interface buffer. Finally, the buffer blasts that data directly into main memory. And once the entire block is transferred, the DMA sends one single interrupt to tell the CPU, hey, the entire job is done. Now, what's really interesting about this next concept is how we contrast the two DMA transfer strategies, which depend entirely on the hardware buffer size. If the buffer is small, it uses cycle stealing. The disk fills the tiny buffer, the DMA steals just one system bus cycle from the CPU to transfer that single word to memory, and then gives the bus right back. It happens word by word. But if the DMA has a large buffer, it uses burst mode. It waits for the slow disk to fill up a huge buffer, and then takes over the bus to transfer the entire block of data in one massive, uninterrupted bulk burst. This brings us to a critical look at system timing metrics, highlighting the real-world impact on latency. We essentially have two phases here: preparation time and transfer time. During preparation time, the slow disk is filling the DMA's buffer. In this phase, the system bus is completely free, meaning the CPU is happily executing other tasks. It's fully busy working. But during transfer time, when the buffer quickly dumps to main memory, the DMA is actively using the system bus. For that brief moment, the CPU is momentarily blocked from using the bus. Understanding these distinct phases is exactly how system architects calculate real-world latency and optimize system throughput. Which leads us to a fascinating question for the future. We've spent decades building these complex translators, interfaces, and DMA controllers entirely because peripherals were so much slower than CPUs. But as we develop ultra-fast solid-state drives, high-speed fiber optics, and incredibly smart peripheral devices, as they become faster and smarter, will the CPU eventually become the bottleneck? Thank you so much for joining this structural deep dive today. I hope this explainer illuminated the hidden communication crisis inside your system and leaves you eager to explore more of the fascinating world of computer architecture.
If you enjoyed this video and learned something new, like this video, comment your favorite programming language, subscribe to Future Break Coder, because many exciting coding and futuristic tech videos are coming.